hearty welcome to our guest, Professor Sanjeev Dwivedi sir, and to all the participants. A brief description about Professor Sanjeev Dwivedi sir is, sir has a strong record of accomplishment in research area of green technologies by his contribution in power electronics and control of electric drives. He has more than 30 years of experience in the design, research, administration, development, coaching, engineering, and commercialization of power electronics products. He is working with Danfoss Drive Intelligence Power Electronics at Denmark from last 13 plus years or at different positions and assignments from industrial electronic applications to green technologies. He has demonstrated his leadership in developing technologies and products from concept to commercialization by his 7 international patents and 4 secrets of business trade. He was awarded by the CEO of Danfoss by MOTM Award for his business idea, which is subsequently developed from a concept idea and now generating revenue stream. Professor Sanjit has also received the most prestigious award in power electronics in India by the IETE Bimal Bose Award for Leadership in Power Electronics. He was an honorary adjunct professor at power electronics at Curtin University, Perth, Australia for a period of 2 years from 2016 to 18. Sir will be giving us a talk on synergies between green technologies and power electronics. It is our proud privilege to have you, sir. Over to you, sir.
Thank you very much, madam. And I take privilege to speak on it. So let me know when you see my presentation, and then
Yes, sir.
we'll start talking. Can you see it?
Yes, sir. We can see it.
Yeah, and then I will change the slide and make sure that every
Yes.
participant can see the change.
Yes.
You can see the
Yes,
slide
sir. It is
also.
changing, sir. Yes,
Okay,
sir.
that's welcome everybody to the faculty development program, and that is organized on the topic recent trend in renewable energy. And my today's talk is centered on synergies between green technology and power electronics. Little brief about my background. I'm living in Grosten, that is the summer capital of Denmark. And Germany is around 15 kilometers from here. So we are in the southern region of the Denmark. I'm graduated from Government Engineering College, Jabalpur. I did my master's from IIT Roorkee with gold medal and MSc Engineering from South Denmark University in Innovation and Business. Doctoral in Power Electronics and Electrical Machine and Control of Drive from IIT Delhi. Executive leadership from MIT Boston. Few affiliation like Fellow of IIT UK and Senior Member IEEE. Few volunteer assignment, and I'm editor of IEEE Transaction on Industrial Electronics, and I have completed my term of 6 years in IEEE Transaction of Mechatronics as a technical editor this year. I'm also volunteering industry as the industry relation coordinator of IEEE Denmark section. And in fact, we are organizing a this institute, academia and industry technology transfer event that is organized on 8th October. I will share the link so you can participate in it. There are some speakers from around the globe on that, from Canada and from Denmark and some other countries. There was some award on my name. Thank you so much to Danfoss and IET. I'm working here in Danfoss Drive since 2008. This is my email address. If anybody interested after follow-up of my talk or having subsequent questions, they can write to me. Main interest in control engineering, control of electrical drives, drive intelligence. This is the new you can say area where it is augmented with the industry 4.0. That's a new revolution in the condition-based monitoring and asset management. So in Danfoss, we are having a new department on this area. And then condition monitoring of electrical machine. This is my workplace. This is known as, you see that in this part, there is somewhere my office. This is my company headquarters located 40 kilometers from this place. This is known as Nordborg. And you see here, this is the solar plant supplying required energy to local facility. And this is the company headquarters, 13-story building here. And there are some more division, like we are a company with having greater responsibility for climate solutions. So we are working with heating solution, cooling solution, and then infrastructure solution with Danfoss uh, power, agriculture equipment, and other infrastructure equipment. So we are having three divisions here. One is heating, one is cooling, and one is power solution. And you can see that is the Baltic Sea. That's the area. So before starting my presentation, who we are? We are 100% focused on developing, manufacturing, and supplying AC drives. Danfoss Drive is a world leader and first mover in variable speed control of electric drive. In fact, we have invented and we have commercialized this variable frequency control in 1968, way before any other manufacturer like ABB and Siemens or any other. And in 2014, another milestone comes in the history of Danfoss when a spin-out company from ABB, Vacon, based in Finland, and another reputed company in the variable frequency drive, that we merged together and formed the largest company in the industry. Together, we will continue to be driven by a passion to develop, manufacture, and provide the most versatile variable frequency drive in the world. And our capabilities are, we can control any motor from the power size of 180 watt to 5.3 megawatt, and even in the medium voltage range. I have planned my presentation in this way. We will introduce the topic, why green energy is needed and why we are striving for this solution. And we will look into the global mega trend and how Danfoss is contributing for that. Then we will go through the green energy sources like solar, wind, and biofuel and green hydrogen. I will explain uh, what are the power electronics component behind it in the brief. Then we will look into the trend in solar and wind energy research. Afterward, we will jump in synergies between green energy and power electronics. And we'll see the rationale why I'm saying that synergy between green energy and power electronics. Last but not the least, recent trend in motor control technology, and we will dive through some of the interesting result of new control method like direct power control, and we will also go through a new type of motor which is having efficiency more than 96% and having, this is a revolution in the electrical drive industry. That's a contactless synchronous motor, separately excited synchronous motor. And that is used already in General Motor and BMW version i3 to i6. We can see here what are the global mega trend that are transforming our world. It started from the urbanization. You know that world population is increasing in a faster rate, and for that people are moving from the underdeveloped part of the or the remote part of the uh, different countries to the cities with the better facilities and better infrastructure, and that is increasing the demand on the urbanization efforts. And this is the one of the major change, and here we need solution which is eco-friendly and which is not harming our climate. Then we see that climate change. This is coming to the various industry, various power plant, and various emission from the conventional gasoline-based car, and there also we see a lot of efforts are uh, made, and we as a Danfoss, we also care, and we made a separate division on this climate solutions nowadays. And then the next year we are organizing a international energy conference that is sponsored by IEA. That is the biggest conference in this topic in the world. And that's next one is the food supply. As you know, the local foods, some part of the world they are underprivileged, and some part of world they are the buyer, and some part they are making effort to generate the food. And during this production to distribution and supply network, efficiencies are needed, and for that Danfoss is providing a lot of engineering solutions so that not only the product can be food product can be stored, but they are safely transferred from one place to another place, and then they are available to the consumers. And then electrification journey. So if you name surface transport, we are having a division which is working on the electrical vehicles for off-road and on-road applications. And if you talk about marine application, then we are also having the solution for marine propulsion. And in fact, we have provided all the consultancy and all the uh, product needed for that to make 100% electric ferry. And additionally, we can have a possibility to make these uh, port equipped with the electricity chargers, and then providing these uh, high current requirement and uninterrupted power supply and good power quality for feeding the local ferries and ships. Then finally, this is the digitalization journey. As you know, uh, this industry 4.0 that is demanding that all the asset they should run efficiently, and they should have energy efficiency as well as uh, output from these asset. uh, it must be uninterruptible, and then the cost needed for the repair and maintenance that should be also minimized, and then the analytics must be there in the connected world. So Danfoss is supporting all the infrastructure needed for the data centers, and in fact, in Danfoss, we are trying to produce electricity, green electricity, and we are providing all the equipment needed for maintaining the uh, energy efficient environment for the data center, like HVAC equipment or uh, clean air supply or backup and power supply for the big servers. So if you look on the global mega trend, Danfoss is working for the solutions to make our future safe. Now talking about why green energy technology. In the 2015 Paris Agreement, nations around the world agreed that rapid decarbonization is needed to prevent the dangerous impact of climate change. Then in 2018, the Intergovernmental Panel on Climate Change that report that global warming of 1.5 degrees centigrade showed that the need to cut greenhouse gas emission rapidly is even more urgent than previously thought. The window of opportunity is closing fast for meaningful action to limit the planet's increase in temperature and to counter the global climate crisis. And there are symptoms you see around. We never thought of this heat wave in what we saw a few months back in US. A lot of people died, and the country with all the developed solution, they are the helpless, and that is due to this global climate crisis. And we are going to see more and more this type of hazardous events. Therefore, policymakers must increase their effort to reduce or eliminate emission in all economic activities. And options that would deliver only partial emission reduction are not sufficient. Please mind that it's very powerful um, uh, statement. Options that would deliver only partial emission reductions are not sufficient, and that's why our Prime Minister, if you pay attention to his speech, he told $1 trillion economy he will make on the hydrogen solution. And because if we live on that mindset that partial solution can work and we can slowly reduce, then it is too late and we are not finding any solution. That's why our visionary leader he is having a commitment, and then he's supporting for this idea, and he know what need to be done. The full decarbonization of some industries and transport subsectors is technically and economically challenging, and the current number of solution is limited. These are known as hard to abate sectors. There is, however, common solution for some of these hard to abate sector, and that is the hydrogen produced with renewable energy, also known as the green hydrogen. This is a solution. So being looking on the why green energy solution, we say that alarming issue of climate change. And I will repeat, the window of opportunity is closing fast for meaningful action to limit the planet increase in temperature and to counter the global climate crisis. You see that how much electricity we are generating from the coal, even in India and around the world. So we need to find the green solution for generating the energy. And I will come to the number when we are utilizing the power electronics and drive, how much extra energy we can save or how much extra energy we can produce. So let's dive through the green energy and what is needed from the academia and research community. Due to the environmental issue of carbon dioxide emission and global warming, energy systems worldwide are undergoing a major transformation towards the widespread use of green energy. The electrical power system in a sustainable future will augment the centralized and large grid dependent system of today with distributed small scale, small grid based energy generation system. To achieve this, world will increasingly adopt renewable energy sources. They can be solar, wind, or fuel cell, or any other solution. And as I mentioned in the starting of this presentation, the power electronics is essential for harnessing energy from solar, wind, fuel cell, and other green energy sources in the form of converter, inverter, or DC-DC converter, or solid-state transformer. Power electronics is present everywhere. Whether you talk about harnessing the solar energy by a solar panel, you need a DC-DC converter and an inverter to feed in the grid or to the local load. Similarly, in case of wind, you need to have a generator control by inverter or active rectifier and feed into the grid. So, and then similarly for fuel cell, you need DC-DC converter and DC to AC converter. So you cannot live without the power electronics. And then electrical drive play an important role in increasing energy efficiency of electrical power generated worldwide by conventional or green energy sources. So even as on today, if we replace all the applications which are run by direct online or fixed speed by variable speed, we are having a potential to save 1/10 of the energy around the globe. It's again very powerful statement. So we can augment extra 10% energy worldwide. So so responsibility on power electronics and drive expert part is much more. And this future of green energy system, that depending necessarily on delivering on the three dimension, providing safer, secure, and reliable energy while delivering access to all energy consumers, supplying energy at affordable price. Please put some emphasis on this statement. If you remember that Reliance, uh, Ambani, they have, he told that he will offer by 2025 hydrogen as an energy source and with a unbelievable price of $1 per kg. And when I'm saying $1 per kg, then nobody is able to produce in the world at this rate. And if we want to switch to the green energy sources, and we want it a reliable supply, and yes, really we want to take India to that direction, then we need energy in that affordable price, and we all having responsibility to work for it. Assuring sustainable development. So we have to have our uh, whatever uh, effort we are making for development, they must be sustainable. We need to, if we are developing, we are investing on the road, or we are infrastructure, or we are investing on the smart city project, and there we need to find more and more use of green energy and more uh, use of resources which are sustainable. So this future green energy system, this will evolve massive changes in technical and organization level, together with tremendous technological upgrade in different sector, ranging from energy generation, transmission, and down to the distribution system. And we have seen some of the major initiative by government of India, that uh, we have taken lead on International Solar Alliance, and we are the leader for that, and we are contributing with the Indian Institute of Indian Institute on Solar Energy Research, and they are around the different part of India. We have similar to IIT and NIT, our Solar Research Institute, and their name is solar, but they are doing contemporary and other renewable energy sources research. And of course, in IITs and NITs, we are having renewable energy department. So we see that uh, there are some kind of efforts are already taking place with more pace. These actions constitute a huge science and engineering challenge and demand for expert knowledge in the field to create solutions for a sustainable energy system. And here, a greater responsibility for on us. And when I'm saying the us, then we teachers and researchers, they are having the greater responsibility for it. And this must be economically, environmentally, and socially viable by meeting high security requirement. So this is a future energy system, green energy system for future. Uh, Here it is argument. You see the generating station with the conventional coal-based system, but you also see that a distribution at distribution network we are feeding in by a rooftop solar plant. So that is both uh, conventional energy sources and renewable energy sources that are part of this uh, future in the electric power system. If we looked on the price of energy generated by the green energy sources or renewable energy sources, then we will find a fact which is giving a very promising situation. And then we filled with the joy that now time comes when renewable energy is cheaper than the our conventional energy. There are some numbers you can see that solar PV rooftop residential that's having a comparative cost of $184, and solar PV with thin film utility scale that is a cost of $43 per megawatt hour generation. Wind is $32 and biomass $82, fuel cell $106. So compared to coal, that is $65 per megawatt hour. Gas is lower than this. Wind is the lowest, and solar is having, depending on the which technology you are using, solar will vary on that. And there are a lot of research is going on. There are a lot of scientists working on reducing the price of solar panel and solar power solution. We will go through those curves soon. But before that, let's see this smart grid. That is the reliable source of green energy for a smart city. And we can define it. A smart microgrid is local. It creates energy for itself or nearby customers. A smart microgrid is independent. It can disconnect from the central grid and operate by itself. A smart microgrid is intelligent. The central brain or microgrid controller is where the intelligence originates. So if you see here, a network of solar PV utility plant together with battery storage and wind turbine or wind plant. Additionally, the electrical vehicle charging infrastructure and distributed generation combined heat power cycle system, connected network of other microgrid, and feed in with the weather forecast and the energy market variation. So this network, which is capable to store the excessive energy in the battery, or it can capable to provide the excessive energy to the grid, or it can take the energy from the utility plant or from the green energy sources like solar plant. So this bidirectional power flow based on the energy weather forecast and energy market price variation, and then full resiliency, that is known as a smart grid. And the essential component of a smart grid is again power electronics and drive. I'm showing here in this slide what will be the future secured green energy sources for our next generation. If you look on the number, what is the annual world energy consumption in 2009? I'm going little back and showing from there. So in 2009, our worldwide energy consumption was terawatt year. You know that kilowatt hour. So it is the terawatt and hour to year. So 16 terawatt year. How big this number is? Just calculate and how many zeros are increased. So 16 terawatt year per year rate. That was the consumption in 2009. That is supposed to increase by 75% by 2050, and it will become 28 terawatt year per year. And please see the bubble size that is showing these numbers also. So visual effect. So if you see the baseline of solar, 16 terawatt year per year, that bubble size, then 28 terawatt year per year is this much, the next bubble. And if you look on our reserve fossil fuel, like coal, so we do have only possibility to feed in energy for 900 terawatt year. Uranium only for 990 to 300 terawatt year. Natural gas 215 terawatt year. Oil that is only for 240 terawatt year. Then what should be the energy source of future? Hydro, that's having very limited capability, 3 to 4 terawatt year per year, because you cannot generate the um, hydropower plant and get the energy, because you need physical uh, preferences. You need to have those water source. You need to have that head, necessary head required for it. So there are only few privileged countries which are having this possibility, and India is one of it. Then wind, that is again having very limited capability of 25 to 70 terawatt year per year. But then what? Look on the bubble of solar. That's a 23,000 terawatt year per year. So that's the energy source for the future. And I will show you with some numbers. You will surprise that how fast Indian journey is for the Indian journey and around the world journey is towards harnessing the solar energy. So if you look in the list, some of the world's biggest solar power plant, that is the capacity of 750 or 1000 megawatt or 2000 megawatt, and their first four or first five, they are from the India. So we are leading on this. And if you look on the share of primary energy from the solar, you see these colors and this dark red color that is showing that's more than 1.2% energy that is coming from the solar. And India is one of the fortunate country which is having abundant availability of solar energy, and we are also start harnessing it. And this is the trend. How many number of 1 gigawatt solar plant installed? So it is started from 2010. There were only worldwide installed capacity was around 6 or 7 gigawatt. Or the size of number of 1 gigawatt power plant, that was the 6 or 7 megawatt. But now you see that highest size is going to this 42 gigawatt. So this trend is more and more big power plant, a number of 1 gigawatt markets that's increasing worldwide. And as I told you, the price for solar photovoltaic multi-module that's coming down from $0.63 to $0.19 in terms of price in US dollar per peak watt. So there is a, I think, almost fourth fold decrease in the price, and that's a good sign, and that's why solar energy is popularized. If you look on the carbon neutrality, if you compare with the coal, 1,000 gram CO2 equivalent per kilowatt hour, then you'll see that wind is having only 10 gram CO2 emission per kilowatt hour, and photovoltaic is 40 gram carbon dioxide equivalent per kilowatt hour. And if in numbers, you see that wind is 100 times cleaner and solar is 25 times cleaner than the conventional coal power plant. So moving from solar to wind energy conversion is the fastest growing source of new electric generation in the world, and it is expected to remain same. At the end of 2010, the installed wind capacity stand at close to 200,000 megawatt, doubling since 1999, and it could reach close to 800,000 megawatt by the end of 2021. World is observing growth rate more than 10% each year. This is phenomenal. This is phenomenal. Today, 5% of the world electricity comes from the wind power. And you see this journey, it started somewhere from nowhere until 2000, 18,000 megawatt. And now going sky high, like in 2019, 650 megawatt. And as I told earlier, that it is predicted that 800,000 megawatt in 2021. So what are the recent trend in wind energy system? Harnessing wind energy for electric power generation is an area of great research interest, and emphasis is given to the cost-effective utilization of this energy resource for quality and reliable power supply. And Denmark is a fortunate country which having abundant availability of the wind, and they are having one of the world biggest company who are working in the wind sector, namely Ørsted, Vestas, and also Siemens Gamesa, and they are providing their leadership for technology development and providing the best solution around the globe for onshore or offshore wind energy plant. During the last 2 decades, wind turbine has been developed in size from 20 kilowatt to 12 megawatt, while even larger wind turbine are under investigation. A lot of different concepts have been developed and tested. One important development is on the electrical machines as generator, where new concepts also have been industrially implemented. I will show you a comparison where you see that what happened in the past, what is happening now, and what is going to happen in the future. And when I'm talking about the future, that these pilot projects are already running either in Denmark Technical University or some UK university, or research is taking in the IITs in India, and that is towards the superconductor based generator to have the highest possible efficiency, because every every drop of energy is saved from the generator. That is the constant energy source, and it's kind of a revenue. So saving the energy saving the losses, that converted directly to the profit for the energy plant. So in important issue for wind energy efficiency, and efficiency is important when comparing different system, because losses reduce the average power produced by the wind energy converter, and therefore they reduce income. The various wind energy converter system that are able to obtain maximum power output for varying speed, wind turbine and generator adaptation should be also taken into account. The generator choice is based on the turbine size and the wind class. This is the very interesting slide, and here I will tell you that this doubly fed asynchronous generator, that was a very popular topology in 90s, and it was up to 1.5 megawatt to 3 megawatt. That was the low cost mature technology, but it suffered from the gear failure and then poor power quality. And then somewhere in 2005, power size was increased from 2 to 4 megawatt, and then topology comes with the permanent magnet synchronous generator and direct drive or geared, and they were large, heavy, difficult to transport. Weight was more because of the power size, and then this technology with the permanent magnet and all those. Then comes this high temperature superconductor based generator. So this 5 to 10 megawatt power size, and they are having greater power quality, efficient at all load, and small light, and no care. And there are some pilot projects running in UK, and their research is going on in DTU, and they are in development stage. So there is a lot. We are going to hear more and more in the coming year. And you see that cost of energy is reduced. So we are saving 20% power size. So same size wind turbine can produce this volume and dimensions, they can be reduced by 20%. These are some comparison showing how this green technology are produced worldwide. And here comparison is between hydro, wind, bioenergy, solar energy, and geothermal energy. So if you look on hydro, that was the 61% out of all renewable energy generation worldwide. Wind was 20%, bioenergy was 8%, solar was 10%, and geothermal was 1%. Here are the numbers. In 2009, the total, this is coming from International uh, Energy Association, uh, their annual report. In 2019, the total amount of electricity generated from renewable was 6,963 terawatt hour. And renewable hydro was having the highest share, 61% of it. And as I told, there were the new, next to this was wind, and next solar, and the least was geothermal and marine. And decomposition of bioenergy generation, which was having around 8% share, out of which 69% comes from the solid biofuel. And just to share you fact that we are having the third biggest city in Denmark, Aarhus, and that city is energy independent. They are producing all their energy from the city waste. So whether it is the consumable or um, wastewater product, so they are treating them to generate the energy in the form of central heating or the this district heating or in terms of electricity. And here you see growth in renewable electricity generation and solar. You see this yellow color. That's having the biggest growth, and wind is also having this comparable growth compared to it. And of course, bioenergy is having the almost constant growth, and similarly, this geothermal compared to 2015 to 2019. So change is highest 12.3% in wind, 22.7% in solar, and hydropower that's almost constant 1.1%, and then this bioenergy is 5.9%. These are some numbers, and in this table you can see that renewable electricity generation by region. So hydro is highest in the Asia, and next to that in North America. Wind is highest in the Asia again, and next by Europe. So they are very close to each other. Bioenergy is in Europe and Asia. They are all again also comparable in number. But solar, they're particularly leading a lot in Asia compared to Europe and North America. Geothermal, it is in North America and Asia, they are highest. And the marine is, there is less than 1%, so not a, you can say significant figures. As I told you earlier, a new source of renewable energy or the environmental friendly energy, which is saving our planet Earth, that is the green hydrogen. And as you know, hydrogen manufacturing, that is not a new technology. Our industrial plant, our solar plant, and our cement plant and other infrastructure industries, they are using hydrogen, and that is the industrial grade hydrogen, and that is known as blue hydrogen. But when we are producing hydrogen solely by using the renewable energy or the green energy, then this hydrogen is known as the green hydrogen. And then component used for it, they are the electrolyzer, and then consuming this hydrogen in terms of electricity, that is the uh, component that change it, that is the fuel energy, this fuel cell, and then the power electronics component like DC-DC converter and DC to AC inverter. So there are some fact. It was predictable that green hydrogen should receive a new wave of attention from government, policymaker, energy sector stakeholder, and even the general public. So government has taken their initiative. It is now the energy sector stakeholder and general public, they have to take their role. And unprecedented number of report, news article, webinar, and event in the last 2 years have touched upon the topic, but the development of green hydrogen sector is itself is still at very early stage. Every year, around 120 million tons of hydrogen are produced globally, mostly from fossil gas and coal, that is known as the grey hydrogen, while together account for 95% of global production. Hydrogen used for crude oil refinery and for ammonia and methanol synthesis represent almost 75% of hydrogen consumption. So biggest consumer is the ammonia, and you know that ammonia is used for the agriculture sector as a essential component of fertilizer, ammonium nitrate. So if we can produce this ammonia through green hydrogen, then also not only the energy needed for electricity or district heating or cooling, but also for the food food chain also, because that's a form of we are accumulating, we are producing blue hydrogen and then we are producing ammonia, but in this process we are wasting a lot of energy and we are emitting a lot of carbon dioxide. So if we produce the green hydrogen and we utilize it for the agriculture sector, then again we are saving our planet Earth and we are contributing for safer future for our kids. So the roadmap described by IRENA World Energy Transition Outlook include a major role of green hydrogen in reducing the greenhouse gas emission and making the energy transition possible. According to the roadmap, by 2050, green hydrogen need to have far great dimension than today. Production reaching about 400 megaton, equivalent to 49 exajoule. Producing that much in turn would require a significant scale of electrolyzer, with total installed capacity growing to 5 terawatt. And I will say that being a power electronics community and being a responsible, you can say, responsible for the technology development and research development, we are having greater responsibility on the teacher on this part. We need to do the research on the electrolyzers, scaling down their cost competitive price, and their we need to do the breakthrough in this technology. And I will come to the reason, because if we want to uh, reduce the price of green hydrogen to $1 per kg, then lot need to be done on the electrolyzer research and product development. And it will not a surprise that in coming year you will see a lot of startup, they will start in India and they will do the research on these electrolyzer part. The electricity demand to produce hydrogen reaches close to 21,000 terawatt hour per year by 2050. And achieving these ambitious number will be a major challenge. But this report describes that this challenge can be met through a wide range of policies. Policymakers then have a central role to play and have already have the tool to meet the challenge. Some countries have already introduced a hydrogen strategy and implemented initial policy to support the sector, while new targeted policy are being drafted. Still, for the sector to move from niche to mainstream, more diffuse policies and measures will be needed. Policymakers today can draw early lessons from the trailblazing countries in the green hydrogen sector and from their own experiences of renewable energy policy making in the power, heat, and transport sector. So this slide is showing production and value chain of green hydrogen. You see that hydrogen here that is produced by the green energy sources like solar and wind, and then there is an electrolyzer. This electrolyzer is producing to the green energy. It can be distributed through the tanker, or it can be feed in by compressor to local storage, or feed into the gas network. So this is the production part. And transport, it can be transported by the shipping, or it can be transported by the road, or it can be transported by the pipeline, or stored locally. And transformation, it can be utilized by the transformation, with transformation or without transformation. And when with transformation, it can have capability to capture the carbon. So hydrogen is capturing the carbon and making synthetic fuels or electrofuel, or it can capturing the nitrogen and making the green ammonia, which is later used for industries and for agriculture sector. Individual, they are industry. So as I earlier explained, steel industry or chemical industry or refineries, they need a lot of hydrogen. And in transport sector, shipping, ships, there is a worldwide movement to use the efficient energy inside the ships, and even changing the gasoline or petroleum product based engine to the electric engine, and increasing the efficiency for overall efficiency of the ship. So shipping, aviation, that there is a major advantage if we are using hydrogen as a fuel. Then due to the light weight, we can have extra capacity in the aircraft. And then cars, I think you all are already benefited with Dr. Jain presentation on how hydrogen can be used as alternative fuel for EV. Rail, as you know, from last 5 years, there are more than 100 good trains in Germany. They are running on the hydrogen. Trucks, and this is also a popular choice. So in Norway and Singapore, we see now freight is moving through the hydrogen-based vehicles. And buses, that is also a possibility. Then district heating and power generation, that is also the end use of the green hydrogen. As I told earlier, the price of electrolyzer, that is a vital for green hydrogen production. Can you mute yourself? Who is speaking in between?
Participants, please mute your mic.
Kindly mute yourself.
Narayan, you can forcefully, keep the mic. Mr. Rajesh Kumar.
Sir, I have muted him, sir.
Yes, sir, please, you can continue.
Sir, please, sir, Sanjeev, sir, please continue, sir. I have muted him, sir.
Okay, so hydrogen production cost, depending on the electrolyzer, system cost, electricity price, and operating hour. There are two comparisons. In one comparison, we are talking about the unit cost of electrolyzer varying between $770 to between $200 US per kilowatt to $770 per kilowatt. And then with the fixed electricity price. And another one with the electrolyzer with the fixed minimum cost of $200 per kilowatt with the varying electricity price. On the left side, you see that in order to meet this benchmark price of $1 to $2 per kg hydrogen production price. If we are using electrolyzer system cost of 770 per kilowatt, then you need to run it around 8,000 hour or 7,000 something hour. Whereas if your price is reduced to $200 per kilowatt, then you can achieve the same price at only in the 1,600 something hour. So you can see that how much difference you need to run around 5 times longer in order to get the same price. And these are compared with the gray hydrogen cost, because as I told earlier, we are producing the gray hydrogen for our chemical industry and steel industry and refineries. So industry will not paying extra price because industry is competitive. So there is a greater responsibility on us, technocrat and researcher, that we should develop the price. And why this electrolyzer system cost is varying between $200 per kilowatt to 770 kilowatt, $770 per kilowatt, because here we are having a bigger electrolyzer, and here we are having a smaller compared to different power size. So as you go in a lower size, price will per kilowatt will increase. So this is the major hurdle in the commercialization of green hydrogen, that we don't have cost competitive electrolyzer in the lower power range. And here you see that if we are having electrolyzer system cost that is $200 per kilowatt, then this is the curve, and then the effect of electricity between $10 per megawatt hour to $40 per megawatt hour, that is having influence. And if price is $40 per megawatt hour, it will never settle. So we have to have the electricity price between $10 per megawatt hour to $20 per megawatt hour. So depending on this use, we see that with $10 per megawatt hour price, we can achieve very early. And of course, with the 20 also we can achieve it, but with the 40 we never achieve it. So both we need optimization. We need cheaper electricity as well as cheaper electrolyzer. And then we need to do the research to keep on increasing the efficiency of solar panel, and we need to keep on increasing the power size of wind generator and wind turbine and making system more efficient. And these are the production model. You see, it can be full on-site production. So you are having energy supply generation on the site with the green sources, and you produce hydrogen and then you distribute it. Or you use the irrespective of sources, they are mix of green and our conventional energy sources, using the standard our power system transmission network, and produce the hydrogen. Or we can use the hybrid mode. So we know that when we are producing the green hydrogen or when we are using the conventional mix of conventional and green sources. So there is a switch over between green sources and conventional power system. Here you can see the correlation between the levelized cost of hydrogen and operating hour of a grid connected electrolyzer. So capital infrastructure, that is based on the capacity factor. So if capacity is increased around 30% capacity, it will have a constant capital infrastructure. And operating expenses, capital expenses, capital infrastructure expenses, and then green one is operating expenses. So operating expenses, they are increasing based on the capacity, and it is going from increasing in levelized cost of hydrogen is between $1 to $2. So green one is within the range. And here you see the wind share in percentage, how much percentage of wind we use. And this is the CO2 benefit and gas price increase from blending and converting the gas grid to hydrogen. So if we add gas grid, there is an example. if you are adding, you are reducing 7% CO2 emission, you are blending hydrogen, then there is a 37% increase. And this is the curve showing you gas emission, kilogram carbon dioxide per gigajoule. And then here you are increasing the hydrogen concentration volume from 0% to 100%. And this demonstrates clearly that we can have possibility for blending green hydrogen to the national or our commercial gas grid. So how can power electronics and drive that can combat against climate change? Electrical drivetrains for surface, water, ship and ferries, and air transportation. They are having a great potential for combating against climate change by increasing the energy efficiency and reducing the carbon dioxide and hazardous gas emission. Smart grid, energy storage, and efficient solid state transformer, then they can transform the power system. Efficient converters for harnessing wind, solar, and tidal energy. These are the essential. And energy efficient enhancement through VSD and intelligent drive. And efficient power supply for electrolyzers. Because until past, electrolyzer use the very high DC current and then thyristor-based power supplies. So they are having some issues with the power quality, EMC, and in terms of they were not optimal in energy uses also. So we see that these power electronic supply for electrolyzers, they will gaining momentum, and then people will involve and they will put the effort on it. And these people they belong to power electronics and drive community. And also power supply for harnessing fuel cell energy. So taking the fuel cell output and feeding it to the consumer end in terms of EV, ferries, or aircraft, or feeding into the power system, that also needed efficient and intelligent topologies and utilizing the research in power electronics. Danfoss, they are the world leader in electrification, and they are providing all the solutions like what are the equipment needed for the production of green hydrogen, or they can equip the ferry to convert it from conventional to full electric ferry, or they can provide the drivetrain for on-road and off-road vehicles. So for this electrification, what need to be done? Replacement of traditional combustion engine or hydraulic drive with electrical drive. Why? There is an impact. It impacts a wide range of sector: automotive, marine, hybrid, and all electric vehicles, machine building, heat pump, and in some sector, for example, marine, industrial driver used directly. So in order to in this luxury cruise and cruise ships and big ships, uh, this heating, ventilating, air conditioning supply that can be done through the variable frequency drive, and then there is a tremendous amount of scope to reduce the losses and increase the efficiency. In other applications like automotive, drive are customized due to space, cooling, and reliability requirement. And this e-mobility industry is moving very, very fast. There are some numbers. Today, the transportation sector accounts for 25% of all CO2 emission in Europe. By 2040, more than 50% of all cars will be electric, ferries and truck, and other vehicle also going electrical. But there is already trend that European Union and like our Indian government, they are having, they are already started taking initiative. And in India, I'm proud to share with you that in India, this Delhi-Bombay corridor is the first in the world which will only allow electrical vehicle to run on it. So worldwide initiative and leadership on this direction is already in action. Volkswagen, they are the biggest manufacturer and biggest and reputed manufacturer of Europe in electrical vehicle. They say that last generation of combustion engine to be launched in 2026, and that was the statement of December 2018, way before pandemic crisis. So this might be reduced further. Yeah, you can expect that. And 8.1 million new electrical vehicle will hit the road by 2025. Why all electric transportation? Whether it is surface, marine, or air, fuel economy. So we are having well-to-wheel efficiency enhancement by 100% if we go electric transportation. And I will show the reasoning behind it. Low emission, zero tailpipe emission, fuel cost saving, less expensive to operate than conventional vehicle. Energy security, reduce reliance on imported petroleum. India is paying around 10 to 15 lakhs crore rupees for importing the oil. So that's a significant number in terms of our GDP. And if we can secure this electrical transportation, then we can reduce this number to drastically. Fueling flexibility. You can charge at home or in public. You need not to find the petrol pump and waiting in the petrol pump lines. And for this, following consideration are needed. Purchase cost that can be offset by the fuel saving tax credit and incentives. Public charging infrastructure that is in development. Our Niti Aayog, they have given the white paper and they already started promoting with the incentive to industries that they should develop this infrastructure for the public charging and battery recycling and reuse. So there is also increased emphasis on this part. Now we are going through the number to justify that well to wheel efficiency for electrified journey is double or 100% more efficient. When I'm saying well to wheel, then it's a petroleum well, which is extracting the petroleum down the earth and taking it to the refinery, then taking it to the refinery and taking it to distribution network, to petrol pump, to the gasoline based car. Or it can be our power plant, which is running through this oil or gas, and then electrical power network and going to the charger and feeding to the car. Let's see the numbers. So generation percentage, that is 33% electricity generation efficiency. Transmission efficiency is 94%. So well to tank, that is 31% efficiency. And then, and when I'm saying tank, this is the plug or charging plug. And plug to wheel efficiency for electric vehicle, that is 76%. So overall efficiency is 23%. But if you see the numbers for refineries, that is only 82%, and distribution is 98%. So this is 80%. But pump to wheel efficiency is very, very low, 16%. Overall efficiency is 13%. You see that almost double change in terms of well to wheel efficiency when we look on electrified solution or conventional gasoline-based solution. There are some statistics. Bloomberg, they estimate a significant increase in electric vehicle from 2020. So internal combustion engine or IC base, and then battery electric vehicle, plug-in hybrid electrical vehicle, and all EVs. So these number will showing that percentage sales in 20, that is 3%, but it will grow up to the 55% in the 2040. There is a big trend here that is showing a great increase, and this ICE, that is internal combustion engine based vehicle, they will almost constant. They are not going to increase. Always a question of belief if it is 5%, 10%, or 20% in 2025. But the rate after pandemic rate is showing very promising. And in India, we see that Ola has launched their two-wheeler and also electric two-wheeler, and they are going to so popular. And auto rickshaws from Bajaj and other companies, they are also coming in the market. And EV, Tata has also released it, and Mahindra is on the, they are having in the pipeline. So there are a lot of things are moving in India too in this direction. So we are talking about role of electric drive combat against climate change. I mentioned this heat wave issue in US, which was paralyzing the life and then having a major destruction in terms of resources and human life and a lot of unrest there. So focus on increased energy in both market-driven and policy-driven environment. 20% of world energy is electrical energy. So if you combine energy in terms of heat energy, district heating, and or in terms of industrial uses of electricity, or in the chemical process, or pure electrical. So this 1/5 is the electrical energy. And out of this electrical energy, half electrical energy is used by the motor. So we need for automation or industrial applications, or for EVs, or for HVAC sector, we need motors. So 20% of world energy is electrical energy, and half of it is used by the motor. And almost all motors, 80% means I'm simplifying it. So almost all motors, they are driving fan, pump, or compressors. And these applications, fan, pump, and compressor, they do have a special characteristics that their load is proportional to the square of speed. So they are speed dependent. And by running through fixed speed supply or direct online running them, and not running all the time them to the nominal speed, then we have a lot of energy losses. So if we can employ variable speed drive, we can save 1/10 of global electricity consumption. So this is very big statement. And we are in drive, and first drive, we are committed for getting this change. Some of you might know that we, Danfoss, we are also producing power module and stacks for the wind and the solar and other generating plant. And this journey is started in 1998 when UIT, that's Danfoss startup, they Danfoss Silicon Power in North with 20 employees started production, and this going through the new factory in 2000 to a patented technology of solar power liquid cooling in 2002. Then automotive electronic power steering series production. We already cubed around 30 million electric car around the world with our power module. And then journey goes on with expansion of clean room for 1700 meter square area in 2004 to this electric vehicle and related standard TS certification as first and first unit in 2006 to power stack unit established in 2008, and then another milestone, Sava Power Cooling introduced into the wind turbine in series volume in 2008, 10. And then the next leap of innovation that then first bond buffer technology that is introduced and in the automotive industry with 10 million product in 2012. And in 2016, we supported 25 million car equipped with the Danfoss module. And this is going on, and we now in 2017 we open in USA a new power plant, and again we open a R&D on the silicon carbide competence center in 2018, and this journey is going on. So we are supporting automotive application, hybrid EV and battery EV with 12 volt, 48 volt and high voltage application. And for the battery management, charging application, DC-DC converter and electrical power steering. And these are the industry drives, off-highway, welding, healthcare and battery storage. And these are the renewable wind energy and solar energy. So we are having this IATF 16949 standard that meet strict automotive industry requirement. This power module is electronic switch used in the power conversion and motion control application. We are having a cutting edge technology, and the power stack is high quality power electrical assembly which ensure a maximum efficiency for power conversion, compact and lightweight design for power cooling, modular and scalable design to meet our customer need. These are the key differentiator, customized business model. So for depending on the application and customer, we can offer them a dedicated product, innovative packaging technology, patented liquid cooling technology, and intelligent power module stack, as well as we are chip independent. So we are having multi-sourcing of the chips. These are the some few highly advanced packaging technology we use for decisive differentiation. Danfoss bond buffer. This is a new technology for producing of a power module and arrangement for the bond wire. Then Sava Power for efficient cooling and transfer molding. This is a technology for high reliability and robustness and best possible approach for wide band gap and other high temperature devices. So again, these are the 8%. So you take the 20% of whole electricity generation, 50% of it is a 10%, and around 75% of 10% is you'll reach to this number. AC drive has a potential to save 8% of global electricity consumption by 2040. These are some trends in the motor market. Motor, their efficiency classes, they are going higher and higher, and they are imposing minimum requirement for IE4 and IE5. When I'm saying IE4 and IE5, then we are talking about efficiency in the order of for IE4 around 93% and IE5 around 95%. And European Committee of Manufacturer of Electrical Machine and Power Electronics, they estimated 4% share of IE4 motor by 2020. These are the efficiency policy around the world. You see that we already make IE2 efficiency class mandatory, and IE2 is around 90%, 89%. And Europe, they are committed for IE3, and there are some countries they are still not having any IE recommendation. This is the slide where you see a different perspective of electrical motor and how much energy we can save by increasing the efficiency of electric motor by 0.5% even. There are some comparison between industry motor use in industry plant or HVAC or existing places. So it's in the building heating or cooling or compressors or conveyor belt or some other applications, or in the airport for luggage transportation and other things. But these are the conventional motor, and you see the black numbers. They are around 200 million kilowatt in 2017, and they are going to remain same until 2030. But please focus on this dark red color. That is nowhere in 2017, but already reached to the capacity of conventional application industry motor. They are using inverter. So they already reached to that level. And see the how large or how steep slope is there for red motor. So by 2030, cumulative annual growth rate is 28%. They will reach to 1800 million kilowatt by 2030. And this industrial industry motor use that will remain constant until or the same value 200 million kilowatt. So you can imagine that how many fold, 10-fold increase in the motor. And if you save a tiny efficiency in the motor, then you make a differentiator, and you can make a lot of energy saving. And that's why we need again our focus on the motor design and motor control and optimizing the losses in the drive system. And again, power electronics, that's having role for this. So, and this is also a green energy journey. So green and then these green technologies to support this green energy journey that needed power electronics and drive. So you see how much it is coupled together. These are the various type, and some of them you already know, like asynchronous and synchronous. And then there is a synchronous reluctance motor. There are two variants, that is without magnet and with magnet. Then brushless motor with trapezoidal back EMF and sinusoidal back EMF. And this sinusoidal back EMF is that's having a magnet mounting either on surface or in the interior part. So, or we can define these motor by synchronous and synchronous. And synchronous might be magnet type, so interior or surface magnet, or is partially supported synchronous electrous motor with the magnet, or the synchronous motor with the only reluctance on the road. So this is the another kind of definition. Synchronous motor without magnet and with magnet in the rotor. And without magnet can be a synchronous motor with conventional wound, synchronous reluctance motor, and then you need to add one more motor here. This is the separately excited contactless synchronous motor. I will talk about it, and I think we are having around 15 more minutes or 20 minutes. So I will go a little faster, but we will talk about this new technology, a new type of motor, which is a reality where you are having a synchronous motor, but instead of magnet on the rotor, you are supplying electric power to it from the stator and in the contactless manner. And then this synchronous motor with rotor magnet can be surface, interior, or permanent magnet assisted synchronous electric motor. So if you look on the classification based on magnet and reluctance torque, so from surface SPMSM to synchronous electric motor, the magnet proportion is reduces from highest to lowest. Similarly, this reluctance torque, that is increases from 0 to maximum. So in synchronous electric motor, full torque coming from the reluctance and 0 from the magnet. But in PMS, it's a synchronous electric motor, tiny one coming from the magnet and most one from the reluctance. And in fact, magnet is used to create reluctance saliency ratio, reluctance difference between D axis and Q axis. That primarily purpose of magnet to place them to have ease in the creating this saliency. An interior permanent magnet, torque is coming from both part. So motor technology trend is showing a decade ago, more than a decade ago, the motor choice in the industry was between induction motor and permanent magnet motor. But around 2011, there is a price variation in the magnet, whether it is a neodymium metal or neodymium oxide or praseodymium neodymium oxide or lanthanum oxide. You see the price variation was around 50,000 to 300,000 US dollar per metric ton. So around 6-7 times difference. And this price variation alarm worldwide community. And now there is a quest for the new motor technology, which is not depending on the magnet, because this magnet is coming from the China. And why China? Because US abandoned their these mining project in late 60s and 70s. So, and they need to invest a lot. They need to have wait until 5 or 10 years to develop those cost-effective methods. Whereas China, they invested a lot and they are having a capability now to feed world with this required rare earth magnet. And they try to export the finished product instead of magnet material. And there is a political wishes, and that's why there is a changes in the prices and other things. So kind of indirect control on the magnet supply in the world. And that's why this choice is going for the motor, which is motor technology, which is not depending on the magnet. So there is a slow ramp up, mainly due to the poor power factor for the magnetless motor, like synchronous electrons motor. And alternative is PM assisted synchronous electrons motor, which having a good power factor, a small amount of magnet and possibility to use the ferrite magnet. But challenges related to manufacturing technology and PM assisted synchronous electrons motor is still in early market adoption phase, but certainly not niche anymore because already Danfoss is and our competitor also, they are supporting this control for this motor. Although it is difficult because of the magnetizing characteristics as well as saturation dependent D axis and Q axis inductance. So control is more demanding and algorithm need to update these parameter values for based on the operating point. What are the challenges related to choice of motor technology? The availability of a broad range of motor can be a challenge for user. Selecting a right motor for the application. Drive manufacturer who don't bundle drive and motor need to cover all motor type. Like then FOSS is motor independence. Independent. We are not selling motor. We are selling drive, and we say that you connect any AC drive, our drive motor to our drive, and our drive will detect which motor type it is there. And fortunately, that international patent, I was part of that international patent, where drive is detecting which motor is connected to the connected to it automatically. And then it do the AMA also, automatic motor adaptation. It measure the parameter of automatically. And there are another international patent that's also, I was part of that team who developed that patent, and they are in force, they are active in the US Patent Office and other patent offices in Europe and China and in India. So by that, we are motor independent. So any consumer, any customer can connect his motor, and our drive is capable to detect motor type as well as just to check the parameter, and without feeding in, it can control the motor. And if you see these motor classification based on saliency, D-axis, Q-axis, inductance ratio, as well as ratio between torque produced by the permanent magnet to the total torque. You can place baseline with the induction motor at 1. So synchronous reluctance motor, that is having more saliency compared to induction motor, and all the torque is produced by the salient. So there is no PM motor torque, PM part, permanent magnet torque in the synchronous reluctance motor or induction motor. But PM assisted synchronous reluctance motor, that lies here, and IPM here, and you see that SPM that lies here. So you can say that IPM is having two variant, or even the PM assisted synchronous reluctance motor is also a variant of the IPM. In fact, it is. There is no such special design for this PM assisted synchronous reluctance motor, other than that magnet part is very tiny. It's only using 5% magnet compared to 100% magnet of SPM, or whatever 80%, 70% magnet of IPM. So it's a tiny magnet, but the control, you can say definition of D-axis and Q-axis is different compared to PM motors like IPM and SPM. So what is the D-axis for these PM motor? That is the Q-axis for PM assisted synchronous reluctance motor. So that's the change. We can maybe take this design and motor control part later. This is the historical evolution of drive efficiency for the Danfoss drive. In 1968, we were able to have 91% efficiency. In 1983, it was increased to 95%. 93, it was 96%. And in 95, it reaches to that again 96%, and 2003 it was 97%, and in 2001 we are releasing our new product, and then our efficiency is going higher than it, and it can reach up to the 98% or more than that. And these are the benchmark for a 4 kilowatt drive with 400 volt power supply. But efficiency increases limitation. Higher efficiency can be achieved by lowering commutation losses. There are possible solutions like wideband gap devices with low switching losses, silicon carbide and gallium nitride. But faster switching has an adverse effect on the motor insulation and require an output filter. So an extra losses in the filter, extra cost, and then again an electromagnetic interference that having also issue. But then efficiency challenge that increases opportunity. Analyzing drive efficiency from system perspective instead of component perspective open opportunity. Like if you look on the higher switching frequency, and in some application like chemical plant, you cannot connect drive directly to the motor. You need to have a LC filter in between in order to reduce the rate of rise of voltage and to support the lifetime of connected motor. So, but if you increase the switching frequency, then your design of LC filter, that's so you promising result. You can reduce the size of LC filter. That is compact in size. So system level size of filter is reduced. It means you are reducing the losses. So overall system losses will increase, reduce, as well as price will reduce. and higher integration between drive motor and application lead to possible opportunity. For example, common cooling system. You can have a common cooling system also for the whole system. These are some trained in motor control technique, and I think 10 more minutes. So we'll go a little faster here. So VWAP control, voltage vector control, field oriented control, direct torque control, and direct power control. And most of them, like first two, for sure. First three, for sure, you know very well. This is the classification of control technique of AC motor drive. You can say that scalar-based controller or vector-based controller. And scalar-based controller UIF ratio is constant or current is constant. And vector-based controller, that field-oriented control, feedback linearization control, director control, or passivity-based control. Field-oriented control can be a rotor flux-oriented or stator flux-oriented. Rotor flux-oriented is direct or indirect. And stator flux-oriented, that can be open loop or closed loop flux and torque control. And this direct torque control, that can be a with the space vector modulation or circular flux trajectory or hexagon flux trajectory. I will skip this slide. This is scalar control, and the application is in HVAC for energy saving, because you can run the motor at different speed and you can feed in the required current, unlike the direct online motor where you are reducing the speed by mechanical system, and that mechanical system is energy inefficient and consuming remaining energy which is needed to reduce the speed. So motor is always draw the same power, but it is delivering variable amount of output. This is the voltage vector control. It was the revolution in the drive market. This is the patented technology of Danfoss. And here we are using the steady state motor model to know the required amount of voltage, as well as we are using the load compensator. So if there is a increased demand from load side, then we add in extra voltage, and it is performance is in between vector control and open loop control. And that can be a closed loop also. So if we are having possibility to measure the rotor speed by resolver or absolute or incremental encoder, then we can provide the very accurate closed loop control by this method, voltage vector. And as you know, vector control, we can define it by the Park transformation DQ axis, and we can name them DQ control, where D axis current controller that can take care of magnetizing part of current, and Q axis current controller can take off active demand on the current side. This is the flux vector control, and here you see the speed controller for Q axis current, and the flux controller, which is taking care of motor flux, estimated motor flux from the motor model, and then from the flux needed flux reference, there is a D axis required current. So Q axis and D axis required reference current given to the DQ current controller, and this current controller will feed in with the measured current transformed to D and Q axis, and this current controller regulate these current reference current in terms of comparing with the feedback current and having a control action in terms of PI controller or SMC sliding mode controller or any other expert system with control. And then this required amount of voltage in terms of frequency, magnitude, and angle is fed into the inverter pendulum unit that control the speed of motor. This is some detail of experimental setup for DSP-based implementation of vector control PMSM drive. So motor is here not induction, it is the PM motor, but its position, rotor position is measured by a resolver to digital converter, and Then it is fed into the analog devices motion controller 401, that is the DSP board. And here you are also feeding the measured current of 2 phases, and then you also feed in the DC link voltage, and you provide the reference speed. And here you see this is the reference speed, and then you are having the resolver signal to convert to the position and then to speed. So this is the speed controller. And then from the measured speed, that is the demanded flux, reference flux or D-axis current, and then you feed into the 3-phase reference current generator, and these reference current generator feed into the pendulum current controller, which in turn produce the pulses for the IGBTs of this inverter. And then the required variable frequency, variable voltage output is fed into the permanent magnet synchronous motor. So these are some results for a prototype of 2 kilowatt Parker Hanfin motor. And this first, in the subsequent diagram, you'll see that left side simulation result, right side experimental result. This step in is the reference speed, and then the ramp is the actual speed. And then the next two waveform of phase B and phase C current. So they are on the same scale that you see the one division is 275 radian per second speed, and then current is one division is equal to 5 ampere. So this is showing you 5 ampere. This is the speed reversal response. This one is the load application response. You see that load is applied here and load is removed here. This is the load removal response. This is the direct torque control scheme, and it is taken from our book, which is published from IET Press UK, Modeling, Simulation and Control of Electrical Drive. It is one of the best selling book in electrical drive. And around the globe, IEEE fellows like Professor T.M. Jans, Professor M.F. Rahman, who is also IEEE fellow, and Professor Radu from University of Padova in Italy, again IEEE fellow, and then Lennart Hansfors, senior scientist in ABB Sweden, and Rahul Kanchan, who is also Dr. Rahul Kanchan, who is also a senior scientist in ABB, and many other professors around the globe. They written the chapter, and this book is highly useful for the researcher in power electronics and drive. So you can refer it, and I shown it in my reference in the end. And this diagram, why I've given the reference, because this diagram is shared by the Rahul Kanchan, Dr. Rahul Kanchan, and it is in our book, and it is directly taken from the ABB with their permission. So what is the change between vector control and direct control here? You see that there is a speed controller loop, and then there is a speed dependent flux controller loop. So there is a reference flux and actual flux, a reference torque and actual torque, and that is fed to torque comparator and flux comparator. An output of flux comparator and torque comparator, that is fed into optimal switching logic or optimal voltage vector generator. And instead of pendulum signal, we are feeding in directly which switch should be on, which switch should be off in out of these 3 leg. That command is fed to the inverter. And that way we are having a faster control of motor. This is the DTC control scheme of ABB. It can be torque reference or it can be speed reference. When it is fed in from the speed loop and with PI controller, then it is a output of it is the torque reference, but it can directly a torque reference, which is the example of electrical vehicle. There we are not controlling the speed, but we are pedaling the reference torque, and that based on our judgment, user judgment or expert system judgment, or autonomous vehicle with this artificial intelligence base. There we change this reference, and then this flux reference can be fed in through energy optimization algorithm or flux breaking algorithm. So energy optimization is normal use, and flux breaking is when we are stopping the motor. We need to achieve it as fast as possible. So there is a means that we can consume, we can increase the current in the stator in a way that it will not affect the increase in speed, or it can further support the increased losses. So stored energy in mechanical system is consumed in the stator, and that is done by only increasing the magnetizing part of current. So there is no such torque change, but losses are increased, and then the stored energy is consumed, and the motor stator act as a resistive load. And here you see the torque and flux comparator and optimal pulse selector. So these are the result. Speed, you see that speed response, flux response, then torque response, and this circular trajectory of flux between alpha and beta axis. And this is with the flux comparator with 5% band. But if you reduce the band by 2%, then you see the performance is improved. Ripple are reduced. You see that torque ripple is reduced, and flux is also circular, and even the torque is also more smooth. This is the diagram showing you how DTC for PMSM drive. The same, you are having resolver signal feedback, then current signal feedback, and then you are using BMC 401 and using the algorithm to this flux comparator and torque comparator, and then optimal voltage vector selector to find the optimum gate pulses sequence and feed into the gate driver, which in turn control the switches of the inverter. These are some results, and again, for the same motor, and left side is simulated result, right side is the experimental result for ramping up or starting response. I think I was wrong. And this one is the speed reversal response. This one is the load application response. This one is the load removal response. This one is the steady state response. And these are the flux and current in alpha and beta axis. The circular trajectory of stator flux. These are some results with different controller, and I will skip sliding mode controller, hybrid speed controller, and jump to the direct power control. So what is the difference in direct torque control and direct power control? In direct torque control, we are having the hysteresis band around torque error and flux error. But in direct power control, we are having reference real power and reference reactive power. And based on the reference real power and reference reactive power, we can have accurately control of speed as well as accurately control of power factor. So how we'll achieve this reference real power? It's output of speed controller multiplied by the speed. That's giving you the reference real power. And then based on this real power, we have certain rule for power factor, and then we calculate the proportion of reactive power required. So that is the logic. From the torque controller output and from the actual speed, we calculate the real power reference real power, and from this and then required power factor, we calculate the reference reactive power. And once real and reactive reference power is obtained, we know that what current and voltage we are feeding to the motor. So in phase component of voltage and current is real power, and quadrature component is reactive power. So we are having very accurate measurement of feeded real and reactive power. And that way we can make a loop in terms of real and reactive power, or we convert the reference real power and reference reactive power to the reference Q axis and reference D axis current. And then we are using conventional current controller, and then we are having this greater dynamics in the motor control. There is one student in IIT Roorkee who is doing PhD under me and Professor Pathak. He's working towards this topology, and he's going to submit his PhD in the next couple of months, maybe in November or December. And he already opened up his startup in IIT Roorkee Incubation Center. In this convocation, this startup was named by the director, Professor Chaturvedi. That startup name is HMB Drives. So there is a lot of things moving on this control technique. These are some experimental results where this fuzzy expert system is used for reactive power reference generation, and it is particularly useful for the EV, where power factor is giving you a lot of values. I will not go on this fuzzy logic part and then the simulation part. I will just show you some results. So with constant rotor flux operation, you see that rotor speed and rotor flux and then torque, and then motor current, and then develop the speed. And on constant power operation, you can see that these result was these were experimental investigations. So this is the speed feedback, speed response, flux response, this is the torque response, and this is the current response. And this is the constant power factor operation. You see that power factor is achieved in between 0.2 to 0.6 and in that range. So I promise you to give you, although time is very tight, but I will give you the glimpses of this contactless synchronous motor. This is the for the next generation EV. This is the revolution in terms of drivetrain technology. So what we are doing, we are using the conventional synchronous motor, and then we are removing the slip ring and brushes from the rotor circuit, and we are connecting a inductive link, high frequency inductive link voltage receiver and a rectifier unit in the rotor. And this high frequency inductive link is fed supply from the stator side through a different inverter. I will show with the diagram later, but just to give you some brainstorming before starting it. So you remove the rotor brushes and carbon part. Instead of you connect it the inductive link like a wireless charging of electrical vehicle. You are having an inductive coupling and with the air gap. So and this inductive coupling receiver part is on the rotor, and transmitter part is power transmitter part is on the stator. So stator is controlled by three-phase inverter, as well as stator is equipped with the separate high frequency supply so it can feed in the high frequency inductive link, and this link is coupled with the rotor, and rotor receive the required power, and that is the revolution. And BMW started from many years until now. It was a secret, but now it is in public domain. And General Motors, they are also using this technology. The only difference is how they are linking this power and what type of rotary transformer they are using. So, and the reason behind it, we want a dysprosium magnet-free scope or any magnet-free scope. So if we see the advantage of wound rotor synchronous motor, they are plenty, because this technology is mature, and only the copper price and only iron price, and then that way we can streamline the production, as well as we can have optimized cost. So this is the technique. You see, this is the rotor assembly, and this one is the stator assembly. So rotor is moving on top of it, and of course there is air gap in between, but there is a link with the ferrite magnet here, and this ferrite magnet is fed with the high frequency supply. So this is the ferrite core. So this is the inductive core, ferrite core, and through that this rotary secondary will receive the power, And here you see in this diagram, there is a supply part from the stator, and then rotor will receive it. More you can understand from here. See, this is the rotor, and this is the stator, and this is the supply part, ferrite core. And this rotor will move, and it is also having a inductive link, this ferrite core. So when it moves constantly, it receive a supply, and this supply is just then later rectified and then feed into the winding. Or and how we'll excite it? We excite it in a control manner. In a and this part is taken care in the main control algorithm. So, and we need two supply, one for stator and one for this ferrite core. I will not go in detail, but let's go through some visuals. See, this is the conventional AC motor. You are having DC-AC inverter, but for this motor, separately excited synchronous motor, you are having conventional three-phase supply to control the air gap field, as well as you are having rotor current controller and high frequency voltage or high frequency power transfer link. So there is a separate inverter here. So compared to conventional, we are using brushes, but here you can ask me, what is the brushless excitation for turbo alternators? There, what we are doing, we are using a small machine, additional to big alternator or synchronous generator. We are using a small synchronous generator, and then inverted in terms of its field winding is on stator, and armature winding or main field main armature winding on the rotor, and then rotor supply is connected with the power electronics or thyristor unit, and then converted to DC and feed into the supply of main synchronous generator. But here, what we are doing, we are using a rotary transformer, and we don't need any auxiliary alternator on the same sept. So because that increases the weight, cost, and space. And here this rotary transformer feed into the rectifier, and then the rectifier is controlling the current flowing in the rotor winding. And this is the diagram you see. This is your sept, and this is the rotor. This is the rotor. So this rotor moves, and this is the stator. This is the stator part. This is the stator part. So you move in, and then there is always direct link between the stator high frequency supply and rotor induced. And then here you see there are two inverter, one main inverter, another one is rotor current controller. So you feed in this motor with three-phase supply and with rotor current controller. These are some experimental result. You see the green one is the feedback current of phase U, and as you know, we cannot measure the rotor current, but we can measure the what current we are feeding in DC current from the inverter we are feeding into the high frequency link. So, and we estimate the current, what is based on this frequency, based on the inductive circuit, how much current is flowing in the rotor circuit. So we estimate that, and we measure actual current on the DC link, and that way we make a indirect controller which control the rotor current. And this yellow one is the voltage pulse which we are feeding in. So being said that, I will conclude here, and our major takeaways, key takeaways, they are the global mega trend are affecting the planet Earth, and green technology based solution are future of sustainable world against climate change. And we are having a responsibility as power electronics and electrical drive expert, which is an essential component, and have synergies with green technologies in the success journey of green energy transition. And by doing this, we are setting this world safer and full of hope for our next generation. These are some references. I mentioned you my book, these two books. And third one on the electric, this charging technique, wireless and wire-based charging technique for electrical vehicle, that is going to release from the IIT Press UK in next month already. And these are some few patent. I already having published 11 international patent, and 3 are in pipeline. but I made here 4 for reference. Now time for a maybe 2 or 3 quick questions because we are out of time now. So I will say thank you for your patience and ask your question, but I set a ground rule. Whoever asking the question, first tell me your name and your affiliation, and then ask your question.
Thank you, sir. Hello.
Yes, this is time
Hello.
for the question.
Hello.
This is the time for the question.
Yeah, participants, you can ask questions.
So it means everybody is grasped and everybody is understand. Thank you so much. And is there somebody?
Participants, it is a very golden opportunity to ask question because there has a vast experience in drive technology and especially in renewable energy application. So if you have any questions, you may ask.
Sir, I have given permission for the mic. The participants can enable their mic and ask the question. Also, I have given permission for the camera also. If they wanna open the camera and mic,
Hello,
they
sir.
can ask.
Hello.
Yes.
Sir.
Tell me your name and your affiliation.
Hello, sir. Good morning, sir. Myself, Dr. Anand Reddy. I'm working as a professor in the Mechanical Engineering Department at KL Institute of Technology, Hubli, Karnataka, sir.
Yes, welcome, Dr. Anand. Yes, ask your question.
Sir, you have told about the synchronous generator and permanent magnet synchronous generator, sir. So,
yes.
So in case of permanent magnet generators, when we use, we talk about gearless power transmission, sir. The synchronous generators, they need whether they can be operated as a gearless transmission or they have to have a geared operation, sir.
See, it's depending on the topology because you can design your permanent magnet machine with multi-layer rotors, and this gear effect you can get from the magnet design, rotor design. So instead of one layer of rotor, you are having multiple layer. So this was the concept, but as I told you, this magnet part is no longer getting momentum. It was some research in Aalborg University also. There were some research on this direction, but later it got abandoned because of the magnet price and magnet thing. So of course I agree with your question that for direct drive, instead of using the mechanical gear, we can use the magnet effect to modulate the induced EMF or the voltage. But this is not getting momentum. This technology is not.
So the thing is that the required torque for gearless power transmission, if you go for magnetic generator, it will be less compared to the synchronous generator and geared operation.
But you know that geared operation is no longer that's a very useful or in terms of energy efficiency and reliability, and then lifetime of power generation through renewal. That is not a popular choice. So there is a more and more if efforts are taking place in terms of can we use the matrix converter or power electronics topology so that we can harness the maximum power from the variable speed operation, because the purpose of gear part is to keep the speed constant. And
yes, sir.
Why you should keep the speed constant by mechanical means when you are having a possibility in power electronics to keep the output power constant without wasting energy in the mechanical part.
Yes,
so
sir.
I think there is a lot of scope in terms of power electronics, but mechanical engineer having a vast big responsibility to have this low air gap machine design and to reduce the windage losses, and then having the possibility of axial flux machine design and
Yes.
all those parts. So in hand, we need to move our focus from conventional approach to new approach, and then there are synergies. Mechanical engineer can or mechanical expert can support a lot here. Thank you
Yes,
very
sir.
much for
Yes.
your question.
Thank you, sir. Thank you, sir.
Any more questions, participants? I hope we
If
are
there is
not
no
having any-
question,
Yeah,
if
there
there
are
is
no
no
questions.
question, Dr. Singh, then I'm getting late, and then I say thank you
I
very
will
much.
just give you a formal, on the behalf of the Department of Electrical Engineering, University Institute of Technology, and this organizing committee of this event. He has been my PhD supervisor, and I have the fortune area of direct torque control. It was a pleasure hearing you once again. In any time future, we may have some more lectures. Thank you very much once again, sir, for sparing your valuable time in these odd hours of yours. Thanks again, sir. Thank you.
Thank you very much, Professor Singh, for invitation, and thank you very much all participants for listening me and interacting with me. And I will welcome you if you are having further questions, and if you want to connect with me, you can find me in LinkedIn also, and I have shared my email address. So I will be happy to guide you, to talk to you, to be in touch with you. And thank you very much, and bye from my side. Bye bye.